Can you pull the code back up?
Yep. Okay. All right, let's get started. You all got your grades for submission 1 for your project by email. Class as a whole did very well. The one thing I would say, though, is really make sure and pay attention. This is really important. Make sure and pay attention to the verbiage that I wrote for the at the bottom, because it's very possible that, so like let's take student A and student B. It's very possible that student A got a higher grade on submission 1 than student B, but student B doesn't need to do anything to their trust, student A does, okay? For each trust, if you remember on my announcement slide, there was like a checklist that I was going through, like, is it fully dimensioned, does IT equal 0, etc. Does the trust have a joint at the bottom at mid-span, etc. Okay? It's possible you got a really good grade, but you still might need to adjust your trust between now and submittal 2. And for everybody who I think needs to adjust it a little bit, I put some verbiage at the bottom. So please make sure and read that, because I'm trying to make your life a little bit easier for submittal 2. Okay? Submittal 2 is due the Friday before Thanksgiving at 5 p.m. And I want to just really briefly pull up the assignment for submittal 2. And I'll talk about it in some more detail over the next couple weeks and whatnot. But you're going to be uploading what I'll say is at least 3 files, and I'll explain the at least here in a bit. So the 3 files that you're going to need to upload is a masthand file where you've analyzed your trust, a document, quote-unquote document related to your computations, and then a PDF drawing, okay? So I'm going to start off by describing the drawing. So I gave you on Blackboard an example trust layout, so you've got something to follow. But for the drawing, I want the drawing to be submitted as a PDF, and regarding what I want on it, here's essentially the checklist I'm going off of. And again, I gave you an example. I don't care if you use AutoCAD, I don't care if you use MicroStation, it doesn't matter to me, as long as I get a PDF drawing at the end of the day, and this is what I'm looking for, okay? This info right here, okay? So between following this and following the example that I provided on Blackboard, you should have more than enough info to do the PDF, okay? masthand, okay? So I see you running masthand at least 3 times for your project, okay? First off, there is a reason that I want the trust to be determinate, and that is that changing a member size doesn't affect the forces inside the trust, okay? But the other reason I want to use masthand is I don't expect you all to do method of joints or method of sections on this project at all, okay? Because you can just run masthand and get an answer, okay? So I see you running masthand 3 times. Once for a real analysis, once for a virtual analysis, and once at the very end. For the real and virtual analysis, if you haven't yet picked members, it doesn't really matter because, again, changing a member size doesn't affect the forces inside the members. So for your real and virtual analysis, just assign whatever member you want. But at the very end, what I want you to submit is your masthand file with the real loads and the final member selections. And the reason I want you to do that is you should get a value from here, you should get a value from your calculations, and they should be exactly equal, okay? So that's the whole point, is that your masthand file should match what you compute, okay? Now, like I said, for this submittal, I want at least 3 files, okay? I want at least 3 files, and why I'm saying at least 3 is because there's a little bit of wiggle room as to how you do your computations, okay? So at a minimum, you are going to need to submit your computations. If you want to do that by hand, if you want to do it in Excel, that's fine. I imagine most of you are going to do this in Excel. But in addition to your computations, I want to write up explaining, okay, you did submittal 1, you calculated your trust, you calculated your final cost. What would you do if you had to do the project again? Like if you had to go back and redo it, I want a reflection statement. If you want to put that in the Excel file or in your PDF for your computations, that's fine. If you want to upload it as a separate Word document or PDF, that's fine too. So that's why I say I want at least 3 files. It might be 4 if you decide to upload this a little differently. That's fine. It's really up to you. Okay. But what essentially I'm grading you on is your math 10 file, your computations and reflection, and your drawing. Okay. So yeah. Any questions on that? Okay, and that's due Friday at 5 p.m. before Thanksgiving break. And just so everybody's aware, that Friday, the only thing we're doing in class is the project. In other words, I'm going to come in, I'm not taking attendance, and I'm just going to sit here and troubleshoot everybody's project. Because I know you all are busy, and I know that if the project's due 5 p.m. Friday before Thanksgiving break, that might be a 4:37 p.m. problem. That's a joke, not a very funny one. But in all seriousness, I know that up until the last minute, there might be some questions you have, which is why I'm going to make time available that Friday to help troubleshoot with you. I'll be mentioning the project over the next couple weeks. There are a couple things, like some Excel tricks and whatnot, that might make your life a little easier that I'll sort of mention here and there over the next couple weeks and whatnot. But I just wanted to give everybody a big picture of what's going on between now and Thanksgiving for the project. Everybody okay with that? All right. Did everybody get the code? Okay. Everybody good? All right. So with that, let's go ahead and start our topic today. And this topic is different. I'm just going to say it. This one's different. This is probably the maybe the trickiest topic in the class in order to get your head around. Okay, I've heard maybe the best way of describing it is it's a little bit of an inverted topic. It's just a little backwards compared to what we've been doing before. Okay, but we're going to talk about the theory of influence lines, and to sort of motivate the discussion, I drew here 2 problems on the board. Are these the same problem? Are these the same? Is this problem 1 and problem 2? Are they the same problem? I think they are. I think they're the exact same problem. Now, why am I saying that? Well, I have a fixed ended beam, a hinge, a roller, a fixed end, a hinge, a roller, 20 foot, 20 foot, 20 foot, 20 foot. It's the same structure, it's just different loads, right? So yes, it's a different problem, but I want you to think about things maybe a little bit differently. The difference between problem 1 and problem 2 is I took the loads, I just scooched them a little bit. And suddenly it's an entirely different problem. I propose it's not. I propose that there's a different way of looking at things, and this is sort of motivating it. Okay? Up until now, we've only dealt with problems where the loads are stationary. I give you a structure, I put the loads on it, you analyze the structure. We've spent all semester talking about how to draw shear diagrams, draw moment diagrams, compute deflections, compute reactions, all that jazz. But if I take problem 1 and I scooch the loads over, suddenly it's an entirely different problem. Okay? I propose that we've got something to think about now. Moving loads, taking the loads and moving them to a different position on the structure raises a couple of different questions. Okay? The first question is, and probably the most obvious based on how I'm leading the discussion a bit, is can we develop a tool that will help us analyze a structure when the loads move? Okay? And you can probably guess what that tool is. It's an influence line. Okay? That's what an influence line is. And by the way, where would an influence line be most applicable? Like, what is the most obvious case for when structural engineers have to deal with structures that are subjected to loads that move? What's the most obvious case? A bridge, right? So obviously, we need to deal with moving loads on bridges. Now, that's probably the most obvious question, but maybe one that's a little bit more subtle, and I kind of want you to think about this in design land, is can this tool help us figure out the worst case loading? In other words, okay, I've got this 30 kip load. Like, let's say I give you a problem and I say there's a 30 kip load and a 2 kip per foot distributed load. Where do I put that load on the structure to generate the biggest response, the biggest support reaction, the most bending moment, the most shear, etc.? Why would we care about that? Because our role as a structural engineer is not just to analyze, but to design, okay? And we need to know where to put that load to generate the worst case response, and it is that response we need to design for. Does that make sense? Okay, so that tool is called an influence line. Now, before I pull this up, I want everybody to hear the words that are coming out of my mouth right now, okay? I'm going to show you some influence lines. They are not shear diagrams. They are not moment diagrams. I'm going to say that again. Influence lines are not shear and moment diagrams. You know what? I'm going to say it a third time. Influence lines are not shear and moment diagrams, but they look a lot like them, okay? So it's easy to confuse the two. In fact, I would argue that shear and moment diagrams and influence lines are inverses of one another. They're almost opposites, okay? And that'll become clear when we start constructing them and start thinking about them in a little bit more detail, okay? So, let's talk about an influence line. What is an influence line, okay? An influence line is a diagram that we use as structural engineers for assessing moving loads, okay? So we have a structure, the loads move, how do we deal with that? We use an influence line. So, what do? Okay, the first thing that we have to do is, and this is probably the biggest limit of an influence line, is that we have to pick a point of interest. We have to pick something in the structure that we are interested in. Now, an example could be a support reaction. So in other words, for these two problems that I have drawn here on the board, I could draw an influence line for that reaction, the vertical reaction at C. Or I could draw an influence line for the shear right here, or an influence line for the moment right there, or an influence line for the moment reaction here. Okay, I have to pick a point. I have to pick something that I'm interested in. Okay, once I pick that point, I take a load and I move it across the structure. What load do I move? Well, traditionally, you will move a unit load. So think of it as like a 1 kip load that moves across the structure. Okay, and as that load moves across the structure, we will record the response. Now, I'm going to go ahead and say something now. This definition is the most fundamental, basic definition for an influence line, and it will work, okay? But we're going to learn a little trick to make the construction of influence lines a whole lot easier, okay? And that trick is the Muller-Breslau principle, which I'll pull up here in a bit, okay? To give you a basic example of what I'm talking about, let's take a look at this, okay? Let me see if I've got some markers here. Okay, there we go. All right, so let's take a look at this example, okay? So I have a unit load, and I'm going to move this unit load across the structure, and I am interested for this problem to draw an influence line for the reaction at A, okay? So the big thing that you want to keep your eye focused on is the reaction at A. So let me draw something up here on the board. Okay, and so we have a vertical reaction here. We'll assume upward reactions are positive. So AY, BY. Okay, and this dimension is what I have here, 80 foot. Okay, so let's put a coordinate system on this thing. I got a coordinate system up here. So we'll just say Y, X. Or maybe more specifically what we'll do is we'll say, you know, over here, Y, and put, you know, coordinate system down here, X. Sort of the same thing. Doesn't really matter. Okay. So what I'm going to do is I'm going to draw myself a little table right here. And we'll put X values in this column. And we'll put AY values in this column. Okay. So let's just think logically and think easily here. Okay. So let me ask you a question. If I put a load of 1, or 1 tip, right smack dab in the middle of the beam, what is the reaction at A? 0.5. 0.5. Okay. So what would my x coordinate be right here? If I put the load right in the middle? 40. So if I have a 40, this is 1/2. Is everybody okay with that? Okay. All right. Let's look at the extreme case, or one of the extreme cases, I'll say. Let's put the load all the way over here. If I put a unit load atop the roller at B, what is the reaction at A? Zero, right? If I put the load entirely on support B, then the load at support A, then support A is not doing anything, right? So what's the x coordinate right here?
80.
80. And that's 0. So, flip side of that, what if I put the load right there? What if I put the load right there?
0, 1.
So, this is going to be 0. That's going to be 1. So, now let me ask you more generally. If I were to plot this, what would it look like? Like, here's my coordinate system, right? So, this is x equals 0. We'll say this point right here is x equals 80. What does the influence line look like right here? So, you're saying it kind of looks like that?
Yes.
So, this right here is 1.0. That is 1/2. And that is 0. Right? Congratulations. We've just constructed our first influence line. That is the influence line for the reaction at A. Pretty simple, right? Now there's a lot of information packed into this influence line. And we're going to learn how to use influence lines more directly, but a little bit later. But let me say this. I have constructed an influence line for this load. And this influence line tells me what the reaction at A is due to this load present anywhere on the structure, right? I propose that now that I have this influence line, I can tell you the reaction due to any load anywhere. Okay? But we'll get to that later. Some more information that's packed into this. If I have a moving load and my job is to design, let's say, the foundation under this bridge, where do I put that load to generate the worst case response? Well, I shove it over here as much as I can, right? Because that's where my high influence line values are. Make sense? All right. Now, quick pop quiz. This is the influence line for the reaction at A. What does the influence line for the reaction at B look like? Goes that way, right? It'll go like that. It'll cross right here, right? Because right there the reactions are equal. Make sense? Pretty easy, isn't it? It's not too bad, is it? Okay. All right. All right, so let's break this down a little bit. Influence lines for statically determinate structures are always linear. I mean, there's a reason they're called influence lines, okay? And we can get into the proof of that, throughout our discussion here. But for the sake of this, just take my word that if it's a statically determinate structure, influence lines are indeed lines, okay? It is a fact I want burned into the back of your head, okay? If you have an indeterminate structure, that may not be the case. And we'll talk about indeterminate structures near the end of our discussion of influence lines. But for a determinate structure, it's going to be nonlinear, okay? Now, how do we prove this? Or, proving it's fine, but I think what I'm most interested in is I want to develop a process or a a guide to construct influence lines for more complicated structures. This one's easy. This one's a little tricky. So how do I draw an influence line for this? Okay. Is there a way that we can do that? Yes. Okay. And that process is the Muller-Breslau principle. Okay. So let's talk about the Muller-Breslau principle and how it works. Okay. The Muller-Breslau principle is a graphical approach to drawing influence lines. If you remember, when we discussed shear and moment diagrams, I said, okay, here's this theory, and then let's break it down to a more simple graphical approach. And we use that graphical approach to handle some really complicated problems. And so what I want to do is see if we can do something similar for influence lines, and that approach is called the Muller-Breslau principle. Okay? So what it says, I'm going to read the Muller-Breslau principle in detail, and then I'm going to describe how it works. So the Muller-Breslau principle states as follows. The deflected shape of a structure represents, to some scale, the influence line for a force effect if that quantity in question is moved through a small displacement. That is a lot. What does that mean? Okay, here's what it means. So the first thing we're going to do is we're going to have an influence line, and we're going to identify our response of interest. Like, what are you drawing the influence line for? And I would argue with step one, at least when we're first starting out the theory of influence lines, you don't really need to do anything for step one, because I'm going to tell you, draw the influence line for the reaction at C, draw the influence line for the shear at this point, etc. Okay? So you all aren't going to have to do that. I'll do it for you. Okay? Step two, I want you to remove from the structure the ability to resist that response. Okay? Then I want you to move that structure through a unit displacement. And the resulting shape of that structure is an influence line. Let me kind of show you how that works. Simply supported beam. Here's a support, there's the beam. Okay? Now, influence line for the reaction at A. I am going to identify the reaction at A. I am going to remove from the structure the ability to resist that reaction. Then I'm going to take that point and I'm going to move it up one. What does it look like? It looks like that. Does everybody see that? That is the influence line. Okay? So going into that whole proof thing, I said, well, how do we prove that influence lines are linear? If you have a determinate structure and you remove a response, the resulting structure is unstable, so it can't deform, it can't bend. That's why influence lines are linear for determinate structures. Okay? Now, so we're going to start with influence lines for reactions. That's what we're going to start with. Okay? So we're going to use the Muller-Breslau principle along with some just common sense ideas about influence lines to come up with some rules that we can use to make life a little bit easier. So let's start off with just influence lines for reactions. And by the way, these rules that I'm showing you right now are rules for reactions. On Wednesday, I'm going to show you a different set of rules for shear and moment. Okay? So these rules are for reactions. So what do we know? Influence lines for reactions are going to equal 1 at the reaction that we're looking at, and they're going to equal 0 at all other reactions. I mean, think, if I have a load right at B, what's the reaction at B? 1. What's the reaction at A and C? 0. Make sense? If I have a load at C, the reaction at C is 1, A and B are 0. That should make sense. Everybody okay with that? Okay, that's point 1. Point 2, they are lines. No curves, no parabolas. They are lines. Okay? The third is that if you ever have a hinge, that hinge will change the shape of the slope of the influence line. It will change the slope, not change the shape, change the slope. So I'm going to show you these influence lines. These are what they look like. I'm going to see if my my Desmos plot that I made a long time ago, I'm going to see if that is still there, because I made a Desmos plot for this structure. So let's see if this works. I made a little animation here for this. Here we go. Okay. Okay. All right. So for example, okay, I think this will work. This will work. Okay. So I have this structure built over here. Okay. All right. So let's sort of digest what I've got going on here. Okay. So I've got, let's see, I've got support A, support B, support C. Support A, support B, support C. Okay? I have a hinge right here, hinge right here. Okay? So let's draw, for example, the influence line for the reaction at A. Okay? So what I'm going to do is I'm going to remove from the structure the ability to resist the reaction at A. So that support is gone. Okay? Then what I'm going to do is I'm going to pick A up. Okay? Now again, it's got to be straight lines. So this is going to go up, this is going to stay, this is going to stay, and this hinge is going to bend sort of like your elbow. So if I hit play, that's what's going to happen. Does everybody see that? Does everybody see that? So that's what's going to happen there. So this is going to stay at 0, this is going to stay at 0, this is going to hinge, and there's my reaction. Okay? Does that make sense? Everybody okay with that? Any questions on that? So I had to show my little Desmos animation there to sort of make the point. So I think probably the hardest thing about influence lines is being able to visualize that animation. Okay? And so to help with that, I've got two examples that we're going to do. So I've got example 1 and I've got example 2. Now I want to explain something. So I did something a little different with these examples. So I've got example 1A and example 2A. Because what we're going to do is we're going to go back to these examples on Wednesday and we're going to say, okay, tell me what the shear and moment is right here. Tell me what the shear and moment is right here. So I want to go through these in detail for the rest of the lecture. Okay. So we're going to draw the influence lines for these problems. Okay. So let's start off with example 1, okay? And what I'm interested in is, for today, I'm interested in drawing the influence lines for these two reactions, okay? Okay, so let's start off with the influence line for, we'll call it AY, and the influence line for CY. Okay. All right. So let's see if I can, I don't know, simplify this a little bit. Okay. So the example that I showed you on the slide a minute ago, that more complicated one, had an internal hinge, right? Everybody see that? So the beam itself was sort of two rigid segments, like there was from the left end of the hinge and from the hinge to the right end. Okay? This beam is only a single rigid segment. So I propose that both of these influence lines are just going to be a single line. Okay? So let's start off with the influence line for the reaction at A. What is the value of the influence line going to be right here?
1.
1. What's it going to be right here?
0.
0. Okay? So this is going to be 1. This has got to be 0. So now let's see if we can visualize the Muller-Breslau principle. So what does the Muller-Breslau principle say? We pick reaction A and we remove from the structure the ability to resist that. So imagine that vertical support at A, imagine kicking it out of the way, okay? So what's going to happen if I kick that support out? The beam's just going to topple over, right? Then I'm going to take point A and I'm going to pick it up 1 unit. But keep in mind, I didn't get rid of this. So it's almost like a seesaw. It's just going to teeter over that reaction at C, and my influence line is going to look like that. That is the influence line for the reaction at A, period. That's it. Now, before we get to the reaction at C, let's see if we can eyeball some intermediate values. Can anybody tell me what the value is right here at B? What is this value?
1/3.
1/3. How'd you get that?
It's a third of the distance between 0 and 1.
Yeah, so this is 30 foot, this is 10 foot. So that makes that 1/3. What about this value right here?
-1/3.
That's going to be -1/3. Is everybody okay with that? That's easy, right? So, I did AY, one of y'all are going to do CY. Tell me what CY is going to look like.
It's going to start at 0, and at 30 feet it'll go up to 1, and then at 40 feet it'll be 4/3.
It's just going to keep on going up, right? Because if I kick that roller out, but if I keep it pinned here and I pick it up, the whole thing's just going to go up like that, right? So, it's going to look something like that. So that's 0. That's 1. Remember, 0 or 1 at the support of interest, 0 at all other supports. And what's the value right here? What's that value? Say it again? 2/3, and this one is 4/3, right? Let me ask you a question. What is this plus this? What is that plus that? What is that plus that? What about that plus that? What about that? Why is that happening? Because the sum of the forces in the y direction must be 0. I have a unit load going down, so my reactions must sum to 1 going up. There's another check to see if you're drawing your influence lines correctly. Does that make sense? Does this comport with just basic statics? Well, let's see. Let's check that out. Let's consider let's ignore all this influence line nonsense, and let's just put a load at D. So there's that. There's that. Let's put a load right here. Okay? So this dimension here, 30 feet, 10 feet. Let's sum moments at A. This is A. This is C. Let's sum moments at A. So what do I have? I've got 1 times 40 has got to be resisted by something times 30. So we'll assume that CY acts upward. So 40 feet equals CY times 30 feet. So therefore what? CY is 4/3 upward. That's what we got right here, isn't it? Maybe what we'll then do is we'll say let's sum forces in the y direction. And we'll say I got one down. I've got CY is 4/3 up. That's too much up. I need something else going down. AY is probably going down. In other words, 4/3 equals AY plus 1. So therefore, AY is 1/3 down. Is that what we got from our influence line? If the load is at D, what are the reactions? AY is 1/3 down, CY is 4/3 up. That's exactly what statics told us. Does that make sense? Interesting, isn't it? But the idea now is I have the load, I have the reactions everywhere. That's what the influence line tells us. I have the reactions everywhere, due to any load anywhere. What do you think? Shall we do another one? Maybe one that's a little bit trickier? Let's do one that's a little bit trickier. But before I move on, everybody got this? Everybody good? All right, so let's do another one. Oh, this one's fun. I have a 2-span beam, but I got a hinge right here, and I made the dimensions all sorts of messed up. All sorts of messed up. So let's see what we can do here. Okay, so I got 3 reactions that I need to figure out, or 3 influence lines that I need to draw. I'm going to draw the influence lines for all 3 support reactions. Okay, so the influence line for AY, BY, and CY. So let's do that. So we'll put AY up here. Put BY about like that. Put CY about like that. Okay. That's probably good. Okay. So influence line for AY, BY, and CY. Okay. Let's do the easy stuff first. Okay. There should be 3 values you should be able to tell me for every influence line. Let's start with AY. What's the value here?
1.
What's the value here?
0.
What about here?
0.
Okay. So this has got to be 0. This has got to be 0. That's got to be 1. Okay. How many individual beam segments are present in this beam? Is this one single solid beam from span to span, or from end to end? No, there's a hinge here, right? So again, like you got to think about this like it's almost like a kinematic machine. Like the hinges, like there's no deforming. It's just linearly displacing like that. Okay. So I'm asking you now. Let's work through this. Imagine in your head, this is a hinge. I kick out support A. I pick point A and I move it up 1. Tell me what the beam looks like once you've done that. And remember, no curves. There's no curves, and there's no hinges anywhere here or here. That's the only hinge. So what does it look like? What happens when you take point A and you move it up 1? What's it look like?
float down until it gets to the hinge.
Exactly right. What does your influence line for the reaction at A look like? Looks like that. That's 0. That's 0. See, I'm hoping that like this is opening your eyes to some structural behavior in the way you never thought before. For example, if I took this original structure and I put, you know, a load right here, a distributed load there, a load right here, a distributed load there. Because none of these loads are on this side of the hinge, that vertical reaction is 0. Guaranteed. I didn't do any math. All I did is I looked at the influence line. Any loads on this side of the hinge have no impact on the reaction today. None. It's a different way of thinking about things, isn't it? Okay. Let's get rid of all this. Let's do the influence line for the reaction at B. Again, simple values. What's the value here?
0.
1. 0.
All right. Okay. So, imagine taking that beam and kicking out that middle roller. Now keep in mind, it's still pinned here, it's still pinned here. So I've got to pick this structure up such that that displacement's 1. What does the structure look like? What does it look like? Keep in mind, this is where the hinge is. There are no hinges anywhere else.
Start at the hinge and straighten out.
So you're saying that?
No, start at the hinge and then a linear line.
Linear line like this?
Yeah.
Okay, well, how do I get back down to 0? Say,
You go down, like from the 1 to 0, just like you go up, but yeah, you send a line down from 1 to 0.
okay, but here's what I'm saying. There's no hinge here. This is all one solid piece.
So you'll increase from 0 feet to 12 feet at the hinge, and then it'll decrease the rest of the way to 0.
That's what I'm saying is going on. So I'm saying that if I pick this up, the hinge is where it changes direction. Imagine this is like your arm, and that's where your elbow is. If I pick your arm up, it's going to go like that. Does that make sense? This is the only place that it changes slope. Okay? I'm saying that this height is 1, and I'm just saying this height's bigger than 1. Let's see if we can figure out some values. Okay? All right, let's see if we can figure some values out. Can anybody tell me, let's start off with this one. How would you figure out this value right here? This is a line, by the way. So what's the value right there?
0.3.
0.3, how'd you do that?
It's 6 feet out of that 20-foot span there from 0 to 1.
Okay, so this right here, if we do rise over run, so we'll call this, let's call it H1. Okay, so we'll say 1.0 is to 20 as H1 is to 6. Three-tenths. Does everybody see that? So this is 0.3. Okay. What's this? We'll call this H hinge. Somebody else. What is this height? Again, this is a line. It's bigger than 1, right? We agree on that? So if all right, how far is this distance? 20, right? How far is this?
28.
So what's that?
4 over 14. 8 out of 28. 4 over 14.
Well, here, let's carry it out formally. So would you agree that we rise 1 in 20? So we're trying to figure out how much we rise in 28. So would you agree that (28 over 20)? 1.4? I have a feeling I'm blowing folks' minds here a little bit with the slope ratios here. Tell me if I'm going too fast on this. Is everybody okay on this? All right. So let's do our last one. What's the influence line for CY? What's the value here?
0.
About here?
0.
About here?
1.
1. So 0, 0, 1. Now, if everybody's been paying attention, without doing any math, like, well, a little bit of math, what's the value need to be right here?
7/10.
7/10. Why did you say 7/10?
Because it has to equal 1.
The sum of these along every column has to equal 1. So this has got to be 7/10, right? So what does the value have to be right here?
Negative 0.4.
Negative 0.4. Okay, so think about this. I'm pinning the structure here, pinning the structure here, lifting it up 1. It's like a seesaw. It's seesawing around point B. So it's going to lift up like that, and then here's where the elbow is to bring it back up. Does everybody see that? This is where my hinge is. Everything from C on, this is all one solid segment. So this is 0.7 minus 0.4. That's bringing us back to 0. That's the influence line for the reaction at C. So, but there's a lot packed into this. Okay, so think about it. If I want to generate the worst reaction I can think of at support B, where do I put a load? I put it on the hinge. You see that? What about support C? Well, support C is a little tricky because if I put loads on this side of the span, support C has to pull the beam down. If I put loads on this side, it's got to push upward. Does everybody see that? Don't worry, we'll talk about applications of influence lines next week. Right now, I really just want you to focus on trying to construct them. Okay? Did this make sense? Everybody following with me on this? Don't worry, you'll get some practice. So these homework assignments are really quick, but they also require a lot of thought. Okay? It'll only take a minute or two to do, but it'll take a while to think about it. I will see you on Wednesday. New rules, shear and moment diagram for Wednesday. So, or shear and moment influence line. So that's all I got.
These aren't the same as the shear moment diagram.
That's right. As soon as I said it, I was like, ah.